We will now focus on the applications related to antennas, and we will show some examples of simple antennas, and then we will also do some more complicated antennas. In this case, what we are doing now is we will start with a simple horn antenna, which is going to be truncated in a radial manner. So the important thing is the antenna's flare direction is roughly in the x axis. So the along x axis is roughly 31.3 mm, and we are talking about the aperture, this one, the aperture size. So size of aperture is 44.3 mm. So the antenna is going to be fed in this direction. So this is the source direction. It is going to be fed by a waveguide. So it is going to be fed by a waveguide, and the waveguide's width is 22.84 mm. So these are the important things in terms of the cases. So the flared length along the x axis is 31.3 mm. We are talking about an antenna aperture size roughly 44.3 mm, and it is fed by a waveguide width which is 22.84 mm. So what we are using is, we are using a kind of a sine modulated, so sine modulated Gaussian pulse, and whose bandwidth is roughly between 8 to 12.5 gigahertz. So this is the width of the band. It is going to be a sine modulated Gaussian pulse. We are talking about various dimensions here, as we discussed. In most cases, in fact in all cases, our thickness of the absorber, which is basically we are talking about this thickness, is equal to 1 lambda minimum. So these are, in most of the cases, will be roughly 15 layers. So what I have described here is a basic geometry of the problem. With this we are able to see what will be the radius, various radius we are talking about, and the property of this particular antenna, and it is here in red because along the edges we can force certain boundary conditions, whether it is PEC or if you want to be very specific you can also put certain material parameters, but I kept it very simple. So it is basically a kind of a waveguide, but with the opening here, and this thickness I already said will be the waveguide thickness, and the aperture area which is also given for some of the practical applications. This is accurate because we have taken simple horn antenna geometry and we have tried to do the entire computation. So what we are interested is, we are able to compute for various radius of curvatures, and in order to compute the antenna radiation pattern we do a near field to far field Heinen's contour. So this is the points along which this is the contour of the Heinen's plane where we do the near field to far field transformation. So this will give us a kind of radiation pattern what we are looking for to compare it with the experimental value as well, and we can compare various radius of curvatures and its impact. And we are going to truncate it using the radial PML, and the radius of curvature is given along the radial axis, and the angle in which we are doing the transformation is given by the phi value. So locally along each of the cells we might be able to compute what will be the phi. So locally it will be oriented along the x-axis, but globally you can have certain transformation as we discussed earlier. With this we will see what will be the reflected electric field. So what we are computing here is the reflected electric field. The PML layer is starting from here as we discussed, and what you see here is the absorbed field values. So here it is dark circle because the fields are getting absorbed. These are the layers in which the losses are there, and as I increase the radius of curvature I am going larger and larger. So here the PML starts slightly far away. You see again the corners and the outside areas there is an absorbed field. You see less absorbed field on the back side compared to front side because the antenna is oriented in this direction. And when you increase the radius of curvature you will see that the reflection, so you see that these are the reflected fields. So here it is very, very strong compared to here, compared to here, and compared to here. So what is the meaning of this when we compute the radiation pattern? This is what we are going to see here. So here you are seeing the normalized radiation pattern represented in decibels. You will see the main lobe for practical application with R equal to 80 mm, you are able to get for the main lobe pretty much very accurate calculation. You see the influence of the radius of curvature is only noticeable in the side lobes. So the lower side lobes you are able to see the influence of various radius of curvature. This is expected because the radial absorber has reflections coming from the corners, and below 40 dB, minus 40 dB it is not that accurate, but for minus 40 dB this is pretty much a good result. So we can see that we are able to see, and we are talking about a particular frequency 10 gigahertz, we are able to get the main lobe pretty accurate compared to the theoretical value. So here the theoretical value is basically value of the radius of curvature, which is very, very large. Again I should not use the word theoretical value, maybe I should say this is for a case where the reflection is quite low, very low. So this is almost like a plane wave normal incidence. So you can see that it is confirming very well. So we used this as a way, because what happens is the numerical results for larger model is used instead of directly using the antenna chamber measurement, because due to the limitations of the measurements of the chambers, the low level back radiations of the horn antenna are not accurately resolved. So what happens is the low level back radiation in the case of measuring directly from the chambers is not very good. So we are using a numerical result as a theoretical value or a value for which we have to compute. In other words, the performance of this radial truncation or radial PML is quite good for most of the practical application what we need. And this idea we are still working it on a two-dimensional plane where we have taken z direction as a kind of a symmetrical direction. But what you can think of is you can expand this idea to a three-dimensional case. So instead of saying that it is radial only in the xy plane, it can be radial in all the planes. So in that case we are going to go into a spherical radial absorber. So spherical in the sense it is going to be 3 dimension. So this idea is a straightforward expansion or extension from a 2D case with certain additional mathematical complexities. The mathematical complexity comes because we have no longer the z axis symmetry, so we have to compute not only one angle but 2 angles. So this is what we will see in the next slide. In the case of 2D, we only focused on one particular angle of rotation, which is the phi axis, but here you also have the theta. So these two things will give you a unique definition of the radial PML, because by using these two angles and the radius you can compute what will be the loss function. So the loss function is the sigma r function. As you can see, this example is quite helpful for modeling quite complex antennas which are in 3 dimension. This example is very simple, but we are going to talk about a case here, and this case is very complicated geometry because we have totally 2 pairs of 26 windings, and these windings are 0.25 mm in thickness. So it is very fine windings, and these are Archimedean spiral antennas. And what we are interested here is we are interested in finding out the coupling between 2 spiral antennas. One antenna will be a radiating antenna, the other antenna will be the reception antenna. We are interested in seeing what is the coupling between these 2 antennas. And for scattering problems it is a very similar case, and in the case of the low level coupling we are interested in the reflections, because the reflection should be very low, because once the reflections become higher they become dominant source of error for finding out the coupling, because the coupling is quite low. So what we need is an absorbing boundary that is quite good for practical application. Until today this has become a kind of a way to go ahead. Before having the radial PML or spherical PML, what we might do is we might keep the direction or we might keep the direction radial, but we will keep the boundary condition quite far away. So it means that you are doing too much computation, too many cells in between, and these cells are kept only because you wanted to reduce the reflection. There is no other reason why you have to have too many cells. If you keep the boundary condition closer you get so many reflection, and this is quite a difficult problem to compute because you are interested in coupling which is very low in terms of the decibel value. So any source of reflection coming from the boundary should be avoided to the minimum. So in other words you keep them far away, but with the help of the radial boundary condition you can bring the boundary closer and closer, and what is happening here is we are able to make sure that the reflection is quite low for practical application. And what we are interested here is, as you can see, we wanted to make sure that the value of the reflection is low. That is one aspect, and the other aspect is the geometry itself is too complicated for you to do it on a finite difference or any structured methodologies. Finite element will do, but the commercial solvers of finite element at the time when we were trying to solve such problem, they were not good enough. So we have to go for our in-house coding. So that is how we got it, but today maybe the computational solvers are good enough, but still for any commercial solver a problem of this sort is a challenge, because we are talking about the spirals which are quite fine. We are talking of 26 windings of, so let me write it down for you to have an idea. So we have totally 26 windings, so 2 set of windings, and each of the windings the width is 0.25 mm. There are 26 windings but 2 arms are rotating. So these are like something of this sort, and the thickness of these windings are roughly 0.25 mm. Second thing is the substrate thickness is also 0.25 mm. And we are talking about a kind of range of frequency which is operating frequency is 1 to 18 gigahertz. And for most of the applications of this sort we need to go for multiscaling. If you remember, we discussed about multiscaling in the earlier part. So in the case of the balloons, the feed is quite small. So when you talk about lambda minimum, 100 cells per lambda to so this is what is happening. So in the case of the balloon where the feed is there, you are talking about very fine refinement. So we are having 100 cells per lambda, but in the outer areas, in those areas where we are just computing for the sake of having the truncation domain far away, we can go for lambda by 10. And with this what we are interested is we are computing the S21 parameter. One of the antennas is excited with a wideband pulse of the range with pulse width we have discussed, and we are interested in coupling parameters, S21 parameters to the second antenna. So this is what we are computing, and with this problem definition we will see what is happening in the case of the practical simulation. So you see that one of the antennas is excited, the other antenna is kind of being as the coupling, it's getting coupled here. So what we see here is basically a Siller-Muller boundary condition. So instead of having a PML, I am just using Siller-Muller boundary condition to show what is the kind of reflection what we see. If you want to compute the coupling parameter, the coupling coefficient S21, anything of this reflection is practically a disaster. So you can't compute it accurately because there is so much reflection coming from the Siller-Muller boundary condition. So we need to either put this boundary condition really far away so that the reflection is low, or do something using the PML condition. So this is where the spherical radial PML come into play. So what we are doing now is we are computing the value of the PML. So on the left hand side what you see is the domain truncated using a uniaxial spherical PML. So as you can see, the wave reflection here is different to what is happening in the case of Siller-Muller boundary condition. So in the Siller-Muller boundary condition we do not have any PML, we just have a Siller-Muller boundary condition and the waves are getting reflected. In the case of the uniaxial spherical PML, you have a PML sitting right from the point here. So you can see slightly the dotted white lines is the starting point of the PML, and this is roughly 1 lambda, roughly 15 cells which we said for the lowest frequency, and we are talking about truncating the PML using a PEC. So there is still reflection coming, but we need to know what is this reflection. So you can see in the case of the radial PML, the S21 parameter is quite different compared to what you can see here in the Siller-Muller boundary condition. Those zeros are quite missing here because there is so much reflection here. So there is hardly any way you can compute the S21 parameter. But in the case of uniaxial PML you are getting it, but still you do not know what is the actual reflection. So what I am doing here is I am showing you the reflection from the uniaxial PML. I am not worried about Siller-Muller boundary condition because it is clearly not a good thing. So let us focus only on the case of the uniaxial PML, and I am trying to show you is what will be the difference. So in the case of a difference I am computing like before, I take a bigger space. So let me explain this using the slide here. So I will have a very big domain. So this domain is the reference solution, and I have those two antennas here. So this is the exciting antenna, and then this is the antenna where the coupling is happening. So what is happening here is I keep the reference solution as big, but in the case of practical thing I am truncating using a PML that is shorter in terms of the radius. Let us say the thickness of the PML is here. So I use this one as a reference solution such that I make sure that the wave is going from here and then there is some reflection that is coming back. I stop the simulation before the reflection is coming back. So in other words, I make sure that I am only seeing propagating wave, but the reflection is going to be practically 0. So I stop the simulation before the wave reaches the main computation or the main computation what we are interested in. So in that sense I can use this bigger model as a reference model and I can compute the reflection based on the difference between what is happening here minus what is happening here. So that is what I have shown here. So in the example what you are seeing here in the slide, so this is the difference between the bigger model and the smaller model, and I am also getting some kind of reflection, but there is a very good way in which you can see the performance of the PML is and how much amount of the wave is going to be reflected and things of that sort. So what we are seeing here is 2-3 things. One is you have an incidence pulse and this pulse is getting reflected over a period of time, and we have to make sure that our computation is such that we are able to stop the simulation before the reflected pulse comes back. Second thing is we see that clearly the E field magnitude in terms of decibel, in the case of this is the reflected E field, what you see here is quite high in the case of Solow-Muller boundary condition, but in the case of PEC we are seeing it as a kind of a test case where everything that is coming is getting reflected. You can see that the magnitude is slightly larger because there is a superposition and also there is a numerical error, and you are able to see that the wave is getting reflected, whatever is going in is getting reflected. And here what we are seeing is in the case of Solow-Muller boundary condition this reflection is low because some amount of wave is getting absorbed, but still not good enough. In the case of the uniaxial spherical PML we see that the reflected pulse is even lower than the case. So these are the 3 cases. One is everything is getting reflected, which is the red case. In the absorbing boundary condition you see that there is some amount of thing is getting reflected, still there is a bit of an absorption, but this absorption is still in the range of minus 20 decibel. What we need is in the range of minus 50, minus 60 decibel, and this is what we are able to get using the uniaxial spherical PML. And we are able to see also the S21 parameter, the scattering parameter what we are computing, and we are using that using 2 cases, one using the spherical radial PML and we are comparing it using the measurement result from the antenna chamber. So what you see here is as the frequency is increasing the performance is improving for the similar reason that we discussed before, and you see that the results of the spherical PML is quite close to the measurement result. So which is a great relief because you do not want a big disparity between the measurement and the value. So it is one of the biggest advantage of spherical uniaxial PML which we have done, but this is one of the very good results what we have got which matches with measurement result. And not only that, it is able to get those dips, the local zeros what we are interested in, which we are able to compute also very accurately. So with this we are coming to the end of this module. We have discussed simple applications like waveguides, truncation and things of that sort, and we also discussed some complicated problems using very difficult geometry where the multi-scaling factor is very important, and also the PML performance is quite satisfactory compared to the measurement result. With this we have come almost to the end of the finite volume time domain method. We will discuss in the next module the challenges and the limitations of this technique, and also we will discuss about the potential for future research and also the direction to go forward. Thank you.